All right. Hello and welcome everyone here in this room today joining us online. My name is Dennis Cohen and I'm happy to welcome you to today's event in the Social Science Data Lab, a workshop on multiverse analysis by Reinhard Schunck. The Social Science Data Lab is an event series here at the Mannheim Center for European Social Research that provides a platform for researchers to present tools and methods for the collection, management, analysis, and visualization of data in the social sciences. Our speaker today is Reinhard Schunck, professor of sociology at the University of Wuppertal. Reinhard works primarily in the field of social stratification and inequality, concentrating on migration and family-related processes with a focus on quantitative methods. Today's workshop, which Reinhard jointly prepared with Nora Huth-Stöckle, also from the University of Wuppertal, introduces multiverse analysis, which is an approach that tests the sensitivity of statistical results to various design and modeling choices. Before we start, a quick disclaimer on the logistic for today. As usual, we are recording this live stream and we're doing so in active speaker mode. This means that whoever asks a question in this room, that the audio will be recorded. For everyone online, if you ask a question interactively, your audio will be recorded. And in case you activate your camera, your video will be recorded as well. Please feel free to ask your questions at any point during the talk. Those joining us online can simply use the raise hand function in the Zoom chat, and we will then call on you and ask you to unmute yourselves and speak. With that being said, Reinhard, thank you so much for accepting our invitation and for being here today, and the floor is yours.
Yeah, so thank you very much for the invitation, and thank you very much for the kind introduction. I was really happy when you asked me to give a course on multiverse analysis, or when you asked actually Nora and me to give a course on multiverse analysis here today, because Nora and I are pretty excited to talk about it. The slides and all that stuff is joint work by Nora and me, and also some joint work conducted with Johanna. Unfortunately, Nora cannot be here today. She had another appointment that she couldn't move, so it's only me, which is really bad because Nora really introduced me to this method, so she is much more knowledgeable than I am. Okay, so before I start with the talk today, a short disclaimer, what you should not expect. You should not expect a tutorial. I was told when I was invited that I am pretty free to structure the presentation the way that I wanted to. And since it is not that hard, it's more tedious to set up a multiverse analysis. I thought it might be more interesting to give you an overview on the approach, and I think the advantages and also the, let's say, shortcomings or open questions, problematic issues associated with multiverse analysis. If you're interested in conducting a multiverse analysis yourself, I think there are 3 readings that are really good to start with. Obviously, the work of Yuri Simonson and colleagues, specification curve analysis. I am heavily using his do files and adapted them to my needs. There are also, if you're using Stata, other resources that you can use. There are do files programmed by mostly by Christopher Young. And if you're using other programs like R or so, there are also packages which do the same in R. Okay, so that as a disclaimer. Now I'm going to start with a very long quote. I will do this today. I will start with a very long quote, which I just found very good. So I'll give you a second to read the quote. So, and the quote from Ho and Gary King and colleagues from our point of view, sums up the problem quite neatly. Namely that out of all the possible ways to conduct research, we usually only present one. Maybe some robustness analysis, but usually we only present. And Young sees this as a contributor to the crisis in science, which I think is very true. Namely, that the problem that findings cannot be replicated are, amongst other things, due to the fact that there is a lot of model uncertainty. That means we do not give readers, or even ourselves, we do not have a good impression, a good idea on how much our results, our estimates depend on the model choices that we make, on the one hand. And the second point is the lack of transparency, as I will go into more deeply in a second. Many of the choices that are inherent in the research process are implicit, and to some degree they are arbitrary. And sometimes we cannot get rid of this arbitrary element, but it makes a lot of sense to make it transparent, to be open about it. So to make the choices transparent. So the questions that can be addressed with this approach, multiverse analysis, is to give us an idea on how robust our results are on the one hand, and also how to increase transparency in statistical research, quantitative research. I don't know if it's also applicable to qualitative research. I had recently some very interesting discussions with colleagues at my home university who work mostly qualitatively, and yeah, I don't know. Okay. So as I said, one answer to these two problems, to these two challenges is, at least in our point of view, is the so-called multiverse analysis, which is sometimes also called specification curve analysis or multimodal analysis, depending on which author you take, but the idea is always the same. This is obviously related to the many analysts approach, where you have one research question and then you have several teams of researchers who tackle this research question. It is closely related, although it's not necessarily the same. Now, the basic idea, and most of you already know this, is instead of presenting a single analysis and maybe in more or less arbitrary selection of robustness checks where you vary some aspects of the analysis, the basic idea is, instead of doing this, we should present all, in quotes, valid and non-redundant specifications, and make the data analytic decisions as transparent as possible, because this is actually where we will vary how these specifications are defined. Now, we will come back to this, the all valid specifications back later, as it is obviously impossible for a single researcher or even for a team of researchers to present all valid specifications. So there are always some decisions that we have to make which delimit the model space and the space of specifications. Now, the idea is not really new. So in 1997, that was even before I started studying here at University of Mannheim, by the way, There was an econ paper by Sarah E. Martin titled "I just ran 2 million regressions," and this basically was a multiverse analysis. So it's always the economists. Not always the economists, but I mean, the idea is not really completely new. And if we think about it, the methodological background or the methodological underpinnings, or even the philosophy of science background, the ideas is even less so. However, it has gained some attention in the last few years, and as I said, I think it's a promising approach. So, to come back to the problem for a second, the definition of the problem as the authors who have worked in this field define it in one way or the other is that there is an unsystematic approach to the decisions in a research project, in the research practice. And there are numerous decisions that we have to make. On the one hand, this is due to a weak link between theory and empirical specifications or operationalizations. In many cases, I would argue, our theories are not specific enough to tell us really what we have to do. So, for instance, we have a theory about the labor market outcomes of specific groups, but then it's up to us to decide what labor market outcomes we look at. Sometimes the theory is even more specific, so we do know that we want to look at earnings, but in many cases, the link between theory is rather, or it's still distal. There's still some distance between our theoretical conceptions and then the way we operationalize stuff, or the way we set up the research design, to put it even more broadly. So there are numerous ways, even if we have a well-defined research question, on how to approach this research question, the research project. And among the many data analytic decisions to consider are, for instance, like on a very basic level, the design. Even more than I put on the slides. I mean, first of all, we would probably have to decide whether or not we want to do a quantitative or a qualitative design, or whether we want to do both. I don't know how to work qualitatively, so for me, it's always going to be quantitatively, and then I have to decide: is it going to be an experimental or an observational design? I really enjoy working with Johanna because she's an expert in experimental designs. So her approach would probably be to do it. To use an experimental design. My approach has always been using an observational design. Then comes to population or sampling, or even the question, do I collect data myself or do I conduct a secondary data analysis? Then the operationalization, I have some theoretical constructs. How do I operationalize them? We often have multiple ways of operationalizing our theoretical constructs. So that's a decision that we have to make. The data preparation. I mean, you all know how tedious it is and how much work goes into preparing the data for the analysis. It takes much more time than the analysis itself, usually. And there are so many decisions in granting this process. And I mean, we do talk about this a bit, but there are also like restrictions that come from someplace else, maybe the length of the article. And I mean, reviewers don't want to read tedious and very long descriptions of what we've done with the data. However, it's really important because I mean, this then feeds into what comes out at the end. So data preparation is really a big issue. And then covariate selection. I mean, if I do run a model, and if I don't have an experimental design, if I have an observational design, confounding is always like a really big issue. So I really have to spend time about thinking like, how do I have to specify my model in order to not have a misspecified model, which I will still have anyways, but there's a lot of thought which goes into that. And sometimes it's not even clear. So I often encounter the situation, if I think about covariate selection, where it's really unclear to me if a covariate is a confounder or is it a mediator. So it's unclear. And then obviously model selection, like what model do I estimate in order to get the effect estimate that I want to. So there are a lot of decisions that we have to make, and usually what we see in the end, or what we get presented, or what we present, is only one. So some of these decisions are unambiguous, as I already indicated. Some decisions are clear, either because they are directly derivable from the research question, or the theory dictates how we have to go about. However, some of these decisions, and I would say that the majority of these decisions, are kind of arbitrary. There is no clear reason why we would do it in a certain way and not in another way. And this is then what Gell-Mann has called the garden of forking path, or what Simmons and colleagues have called the researcher's degrees of freedom, meaning that there are numerous possibilities to choose from. And in the end, we only choose one. So a very incomplete illustration would then be, as I outlined just a few minutes ago. So we'll have to decide whether or not our design is observational or experimental. Then we'll have to decide on whether or not we want primary data collection or secondary data analysis. If we do secondary data analysis, we might be able to have more than one data set. Usually we only have one data set, so it's a decision not less. And then we have multiple ways of conducting data preparation. We have multiple ways of selecting the covariates, any of which might make sense. We might even, or obviously, not obviously, but sometimes we also have to think about whether or not we want to exclude people or observations for some reason. And then we have to make a model choice. And then this obviously begs the question, like how much do the results that we present in the end depend on all these choices? And is it a good way to go about doing our research if we present only one choice? And even if we think that most researchers have the best intentions, and they are not conducting in any fraudulent behavior or problematic behavior, like no p-hacking, no phishing, even if they have the best intentions, I think this is still to some degree problematic. Good. Now, let's get to the so-called multiverse, as Simonson and colleagues have called it. So Simonson and colleagues define the multiverse as all possible specifications, encompassing, all possible ways of answering a research question, of conducting your research. So within the set of all the possible specifications, there are some specifications which do not make sense, invalid specifications. So it does not make sense to use a design or a model which we know is flawed because we are missing something important, or it's just not applicable, it's not suitable for the data at hand. So the multiverse reduces, or like the selection, the space where we select our models from, reduces to the valid specifications. And then among the set of valid specifications, there are again specifications which are redundant, and we don't need to estimate redundant specifications. So the set that is really interesting is the set of non-redundant specifications. And then what usually happens is we have a selective reporting of only one of those possible specifications. I would argue that we have to delimit it even more, namely like to a set of feasible specifications. It's not possible to estimate all non-redundant specifications, and the set of feasible specifications for one researcher or even for one group is probably much smaller than indicated here. So this is something that we would have to keep in mind. And you will see that it is much smaller when I present you the example in a few minutes from now. This is really interesting if we combine it with like a many analysts approach, or even if we think about just many teams or just two researchers working on the same question. In particular, if the teams or the researchers have different perspectives on the problem, because then this is the right-hand side, because then we really get different takes on the research question, and we might get really different answers, which are nonetheless valid. And if those might not necessarily be different answers, but if we set up a research project, or if we follow a research question as outlined here, on the right side, and we come up with relatively robust results, I think this would give me a lot of confidence that the results are not just arbitrary and depend on some arbitrary model choice or specification. So now I am going to give you an example of how we are using this method in our project. And the research question, one paper we are working on, is concerned with the question: do the returns to physical attractiveness in the German labor market vary by ethnicity and gender? So what we are looking at is starting from the observation that there appears to be a so-called beauty premium in the labor market, that attractive persons compared to non-attractive persons or less attractive person seem to have better labor market outcomes. For instance, higher earnings. There has been, this research has mostly been conducted in the US, so there's really little we know about this in the European context. And in our research project, Johanna and I and our colleagues, we are in particular interested in the intersection of attractiveness, gender, and migration background or ethnicity. Now, I'm not going to show, so there are two disclaimers here. The first is what I'm going to present you here today is rather limited. So there are a lot of choices which we did not vary. And also I'm only going to present you part of the results because of time and stuff. But I hope to give you an idea of how to present the results. Okay. So this here is set. I don't know if you can read it, it's probably too small, but it's an observational design, secondary data analysis. And we are using the German family panel PERFAM, mainly because it has an attractiveness rating for the respondent, and it has an immigrants are oversampled, in particular ethnic Germans, so-called Aussiedler, and respondents of Turkish origin. And we are also only looking at earnings. So this is set, this is something that we do not vary. So hopefully it starts to get interesting here. So let's walk through the data analytic decisions that we made. There might be more. Maybe you have some ideas. My colleagues will be very happy if I rerun the analysis because it always takes time. So you should tell me something now that I should include, and then write me like a mail in 2 weeks. Oh, I forgot. You should also change that so that I can rerun the models again. Okay. So first of all, the outcome. Well, we're looking at earnings. Now, for some of the choices we do, for some of the specifications, we have a preferred choice. So we are looking at our preferred choice, or our preferred outcome are the gross hourly earnings. Gross hourly earnings, well, but gross is a better indicator than net earnings for labor market rewards, or because net earnings also depends on other things than labor market. Okay, so we do have a preference for the gross earnings. However, PERFAM, for some strange reason, decided to collect the gross earnings only every 2 years. PERFAM data is wonderful, but this decision wasn't really smart. Okay, so our preferred choice are the gross earnings. However, this reduces the sample size quite strongly. So the alternative would be to use the net earnings. Then the question is, do we log transform the hourly earnings? If we think that it's a Mincer type equation, more or less a production function, then it's sensible to think that the production factors are that they work in a multiplicative way, and then using the log makes sense. We do think using the log makes sense. So using the log gross hourly earnings is our preferred choice. And then we do have implausible values in the data, where the earnings are implausibly high or implausibly low. This could, for instance, be that the person gave their annual salary and not their monthly salary. We calculated the hourly earnings by looking at work hours and the monthly earnings. So this is it could also, it can just be some measurement error. However, we are not really able to decide whether or not it's measurement error, whether or not it's really implausible, or whether the person really earns a lot or earns not a lot at all. So the question is, do we Winsorize these values? There are some arguments in favor of trimming, but also the other argument would be, well, we don't really know. We cannot really go back and find out. So trimming or not trimming. So we have six different specifications for our outcome variable earnings. The second data analytic decision that we had to make was how to code our treatment, our main independent variable. Now, there are two different ways on how it is done in the literature. We have a continuous rating from 1 to 7, where the respondents are rated by the interviewers at the start of the interview, how attractive they are. And we could either use it in a continuous fashion or in a binary way. Both versions are used. We couldn't really decide what is better. I mean, we could talk about this, but so we're using both. Then group membership, social membership of the social group. So two ways to operationalize that in pair form. We could either work with a migration background, a generational status. With regard to the question of whether or not the respondents or their parents have migrated to Germany, or we could use ethnicity. So different ethnic groups. Could also try to combine that, however, the cell sizes became a bit small, so we use these two specifications. We have some interviewers which are problematic. We looked at the variance. Well, we have clustered data, it's multi-level data. We have some interviewers, and those interviewers conducted interviews. So we have respondents clustered in interviewers, and there are some interviewers which have very little variation on the attractiveness rating of the respondents. And they're all rated as being very, very attractive. So either those interviewers encountered only super attractive respondents, or they maybe didn't like the question, and we do have some indication that this might have been the case. So, the question was, do we include those interviewers or do we exclude them? And it's this. I think it's a similar problem with the implausible earning values. We don't really know what happened at these interviews. It's likely that the ratings that these interviewers gave are not usable. However, that we don't know. So the question was, do we include or exclude the problematic interviewers? A second exclusion problem we had was, do we include the refreshment sample? Perfam included a refreshment sample, and this in the field, and this started right before the COVID pandemic. So we have a mixed mode survey there. All other interviews prior, as far as I recall, were conducted face to face. So it's not really. It wasn't really clear to us whether or not we should include the refreshment sample or not. And age, that is not something that's all often done, including only respondents age 18 or above. And then additional covariance. As I said, we do sometimes have the problem that we are not really sure about the causal status of the covariance. So here, for instance, personality. Now, I have to remind you that we are using this imperfect measure of interviewer ratings of the respondent's attractiveness. So that's not the best rating of attractiveness, but that's a whole other issue. But that's what we can use at the moment. And now it is not implausible to think that some personality characteristics might affect how attractive the interviewer perceives a respondent. On the other hand, the psychological literature strongly suggests that attractiveness elicits reactions from your environment, which can also impact your personality. So personality is probably ambiguous with regard to its causal status. It can be a confounder, but also a mediator. And so it's unclear to us whether or not we should include it in the model or not. We have a similar problem. We have more problems. We have many more problems, but the selection that I present you here, the similar problem that we do have is with cognitive ability. Now, there are some arguments in the literature that there is a correlation. Let's not talk about why, but there might be a correlation between attractiveness, perceived attractiveness and cognitive ability. If this is the case, then ability might be a confounder because it probably affects earnings in some way. We don't have cognitive ability measured in the pair farm data. And then the question is, should we try to use a proxy for cognitive ability? We used a proxy. I mean, we tried to use a proxy. It's imperfect. We are using some measure of interview duration. We are also using height, as through various strange ways correlated with cognitive ability. Yeah.
Positively or negatively?
The R-square is not very high, but positively. Yeah, no, Nan and I just talked about that in the lunch break. Yeah. Yeah. However, not about that. However, it could make including a proxy could make things worse if including the proxy opens up a backdoor path, and then the models are again biased. So it's again like a decision where we decision between two biases, I think. Okay. And yeah, the models are probably still misspecified. So probably still all biased. Okay, and then with regard to the modeling approach itself. So here we limited the modeling approach to regression models, and obviously this is just one choice. One could think about many other approaches, matching estimators or whatsoever. An important thing with the data here is that it's multi-level data, it's clustered data. So we have occasions, interview occasions clustered in respondents, and those respondents are again clustered in interviewers. So the question is, how do we model this dependence? Now, we tried out a few combinations and specifications, and not all combinations are possible, unfortunately. So first thing, classic random effect models, where we estimate models with interviewer and respondent random effects. We could not estimate fixed effects models because physical attractiveness was only measured in wave 1, and then again later in wave 8, but we have to treat it more or less as a time constant characteristic. We don't have enough variation to use fixed effect models. So, and with those random effect models, weighting was not possible. So because of the design of the data, because of the sampling of the data we use, the data should be weighted. However, these models just did not converge if we applied that calibrated design ways. So that's one thing. The second set of models are models where we are interviewer fixed effects models, which also adjusts for the clustering by estimating cluster robust standard errors, which are robust to the three-way clustering. also in time. These models could be weighted. So we use the calibrated design weights. And then for the female respondent, we additionally estimated inverse probability weights predicting their labor force participation. So this is the set of models that we estimated. Okay. Okay. Missing values. We had to use listwise deletion. This is a data-analytic decision where we couldn't do anything else because here the computational time was quite fast. Like these models only took about 30 hours to be estimated. And I mean, if we use multiple imputation and a reasonable set of imputations, this becomes excessive. Okay, so we don't have that many specifications. For the female respondents, we have 1,536 specifications, meaning we have estimated 1,536 models. And for the male respondents, we have fewer models because we did use the inverse probability weights to predict their labor force participation. What I will present to you in a second are now the marginal effects. So, so we basically estimated a model where we use attractiveness and then the group membership and their interaction and covariance. And now we have the marginal effect, meaning the combined effect of attractiveness plus then the group specific effect. So just so that you know what we are presenting here. Good. Now, how do we present the results from a multiverse analysis? There are some summary statistics that one can present. There's a so-called influence analysis you can conduct. Then there are the specification curves, visual graphical display of the results. And then we do have the question of inference, statistical inference with the multiverse analysis. And I will cover these now. So, summary statistics. Well, there are numerous statistics that you can think of. I think useful is the median effect size over all the specifications, the median p-value, and the sign stability, meaning the percentage or the proportion of estimates that have the same sign. And then Young and Holstein also suggested to compute a robustness ratio, which is basically the mean estimate divided by the estimate standard deviation. So it's constructed analogous to a T statistic, but it's kind of problematic because I mean we don't really know the underlying statistical properties. I mean they depend on the model space, so it's not a clear defined test statistic. I'm going to show it to you anyways. Okay. So these are now the results for the log earnings for women. And then here the marginal effects. So, and this actually, okay, here's an error. These are the 1,000 specifications, but no, it's not an error. It's correct. It's obviously correct. Across the 768 specifications, where we distinguish the groups by using ethnicity, the median effect for the association between physical attractiveness and hourly earnings, log hourly earnings is 0.03 log scale. Rather small effect, so approximately 3% higher earnings. And these are then the median effects for the other groups. Median p-values. And the side stability. So we do see that for women without migration background, there seems to be a positive effect. The median p-value is smaller than 0.00, and the sign stability it's like all the signs are positive. For ethnic Germans, the effect is negative. Median p-value is 0.37. Sign stability is about 88%, and so on. So here we do have 12% where the sign is actually, well, most of the signs are negative, but some are positive too. And then this robustness ratio, if you want to interpret it or not.
So you have these two versions of attractiveness. I mean, it's obviously going to affect your coefficient, right? So how do you put them together?
Coefficient is going to be much larger if we use the binary version. So it might make sense to present this in separate tables, which I didn't want to do because of space and time. But obviously that's a good point, and we will see in a second when I show you the so-called influence analysis that this is very obvious. This is obvious that using a binary coefficient, a binary treatment increases the size.
Okay. And for the meeting, you're just taking all the betas. You're not dropping the non-significant.
Exactly.
Betas. Okay.
Using all. Yeah. Yeah. And these are then the results if we use the untransformed earnings, not the log. So I would interpret these findings as there is evidence, robust evidence even, for a positive association between interview-rated attractiveness and earnings for women without migration background, and weak evidence for a positive association in Turkish women. This is up to discussion. Men, the picture is similar with respect to without a migration background. We do have positive effects and high sign stability, low median p-value, relatively high robustness ratio, although it's but I mean, what we do have to take into account is that although Perfam has oversampled Turkish immigrants of Turkish origin and ethnic Germans, the sample sizes are still smaller, so we would expect larger standard errors. So yeah, that's something that we have to take into account. I would say we have robust evidence again here for an association between physical attractiveness and earnings in men without a migration background, and weak evidence for positive association in ethnic men. Good. What Young and Holstein suggested to do is to conduct a so-called influence analysis. That is, to take the estimated betas as a dependent variable, as the outcome, and then just see how the different specification impact these estimated effects. So it gives us an idea about how many model assumptions can be relaxed without overturning the conclusions that we draw, and second, which of the model assumptions are most critical to the results. Now, it's really important to understand that this does not tell us which model assumptions are correct. It only tells us which are influential. So I would not suggest dropping any of these specifications just because we see that they might not be that relevant. It's just that it gives us an idea again of how robust our findings are. So this is now for the women. So the log earnings and ethnicity as the variable or as the indicator which defines the group membership. So in total, these are 304 specifications. And now what Nan already pointed to was, so how do we read this? These are the marginal effects on the estimated coefficient. So as Nan already pointed out, using a binary indicator, using a continuous indicator of attractiveness decreases our effect estimate by more than 0.04. Which makes a whole lot of sense. If you use the 7-point scale, like a 1-point change is expected to result in a smaller change in Y than if you use a binary measure where we distinguish between very attractive respondents on the one hand and then the rest. So what do we see besides that? Well, we see that trimming seems to make a difference. So if we trim the results, meaning if we drop the implausible values, the effect estimates become smaller. So the log gross hourly earnings are the reference, and then if we trim, it becomes smaller, almost by 0.02. And then if you look at the net earnings, well, using the net earnings, also smaller because taxes are deducted, so that makes sense. And then the trimmed, using the trimmed version also makes it smaller. We see that model choice has a large impact. That is something that we have to look into. If we use the interview of fixed effects models, the effect estimates get really bigger. This might be due to weighting because we couldn't weight the random effect models, and this is obviously there is no variation. This is something that we have to look into, and then we at the bottom you see how these choices affect the estimates. So excluding the problematic interviewers increases the mean effect size. Restricting the sample doesn't really make a difference, and including additional controls of unclear causal status decrease the effect size. And now I'm not going to show you. The same for the untransformed earnings because it's not really that interesting. And also I'm not going to show you the results for the man because I mean the mechanism for it's the same because of time. So let's now get to the last point. The specification curves. Now this is something that was proposed by Simonson and colleagues and his article from 2000, their article from 2020. This is basically just a graphical presentation of these results, and they're kind of nice, kind of neat because if you conduct such an influence analysis, it's basically a regression, or it's a regression model, and so you have to assume that all the effects are additive if you don't explicitly test for interactions. And these specification curves are a nice way to visualize the results, where if it were the case, you would see which combinations of specifications produce large or small or significant or insignificant results. I'm not going to present you a lot of figures just for German and Turkish original respondents. So at the top, we have the effects. Each dot or each diamond is a model specification, and they are sorted by effect size. And in red, I have indicated our preferred specification, meaning these are the decisions that we think made the most sense. However, that's a point of discussion that we are actually having in our group, whether or not it makes sense to include this or not, because in some instances we are really not sure if we do have a preferred specification. And then at the bottom, you see the specifications. So each dot is a combination of specifications. And taking it together, putting it together, we have this specification curve. Now it's for women without migration background. And the effect on the dependent variable, the outcome, was the log hourly earnings. The log hourly earnings, exactly. And I mean, what do we see?
Almost for all specification is greater than 0.
Yeah, exactly. So it's for all specifications it's greater than 0. So this, and I mean, we also see that I mean, we do have some insignificant results, but they are like they require a specific combination. We have to have the random effect models. We have to use a continuous measure with additional controls. It also seems to be that it's particularly the that's not really true. So I would say this is rather robust. There's no combination that stands out and drives these results. For Turkish women, looks a bit different. I mean, here again we have the effect sizes and the effect estimates sorted by size. But there are more patches of say statistically insignificant results. And again, we see that that modeling, the random effect models do play a role. Let's say, modeling seems to be okay. Men, not that interesting. And for Turkish men now, as a contrast, we would have been able to find significant negative effects. So we could have written an interesting paper. But no, you can see these are kind of like idiosyncratic combinations. Good. Now to the last point, inference. Before I end the talk. Obviously, it would be nice to get an idea about the statistical inference if we do specification curve analysis or multiverse analysis. So considering the full set of specifications, how inconsistent are the results with another hypothesis of a no effect. Yeah? And I mean, in principle, we can estimate test statistics. So, for instance, we could estimate the median effect, and then test if the estimated median effect estimate is more extreme than you would expect under the null, if the null hypothesis were true. However, like we do have an obvious problem here, namely that it's not possible to derive or to generate a test statistic under the null hypothesis analytically. This I think is intuitively clear because these model specifications are not independent on the one hand, and they're also not part of one single model. So we cannot derive a t statistic or something like that. Depends on the model choice. So what Simonson and colleagues suggested was to generate the test statistic empirically. So basically through a resampling procedure. So what we do is we take the observed data, then we modify the data in a way that the null hypothesis becomes true. So we basically modify the data in a way that the effect is zero. How do you do that? If you have experimental data, you just shuffle treatment. Sure, yeah. That's easy. And if you have non-experimental data, you can actually what you do is you predict. Well, what you basically do is you predict the outcome, and then you do it net of the treatment effect. So
You're subtracting off the
more or less, yes, more or less, exactly, while leaving the rest of the data structure intact. So it's so in this way you just generate a data set where then the beta coefficient for attractiveness in our case is just going to be zero. But it's nicely explained in the well, not in the do files, but it's nicely explained, neatly explained in the 2020 paper from Simonson et al. And then you use this artificially created data set where the null hypothesis is true, is to resample. You draw like a sufficient number of samples, 500 or 1,000, so you just do some bootstrapping, and then you just compare what the resamples have given you. For instance, if you look at the p-value, if you look at the median effect estimate, you can just look at the median effect estimate in your original sample, and then you can look at the median effect estimate in the resamples, in the resampled data set. And then Simonson and colleagues suggest to use the percentage of resample with the test statistic as or more extreme than the observed one as the p-value. And I think that's a good solution. However, the problem is that it's computationally at the moment not feasible for us. Like running this analysis takes about 30 hours. And then if we were to do it only with a set of 100 resamples, which isn't enough, but it just takes too long. So yesterday I attended a talk or an introduction at my university engineers about high performance computing. So maybe this is a solution, but I didn't understand the thing that they talked about. So but I mean, this is the only way forward.
Okay. I can ask, is this with Stata or?
Now this is with Stata, and obviously R is going to be faster and better, but I very much agree. It's gonna R is faster probably, but it's not going to solve this problem. So it's not going to be the case that R is going to be able to estimate these models like in 2 hours or so. It's still going to take some time. Yeah, but we have to switch to R. I know. Oh, we will switch. No, never mind. Okay, so yeah, and this is the same problem we do have with the multiple imputation. So that's really really like a unsatisfactory thing. Also that we have to treat all missing values as missing complete error, which is not true, So okay. So thank you very much for your patience and the time you gave me. I'm at the end of my talk. So we think that that multiverse analysis is a promising approach to increase the transparency of statistical quantitative research, and also to give us a better idea about how robust our results are. And I think it can even make theoretical considerations much more important, because if you make these data analytic decisions more explicit in your research, you're forced to think about them more, instead of just doing it the way that it has always been done. So I think that's a good thing. There are some open questions or some problematic issues that we see. Don't want to get overly enthusiastic. One problem that we definitely see is, if you take the bird's eye view, and if we run all these different models, we have to make sure not to lose sight of the data or a specific model, because it doesn't really help. This brings us to the second point. If we run 1,000 models or even 9 million models, but they're all misspecified. So it's still the garbage in, garbage out. And there it doesn't help, and it could become another method to hide behind. I just ran 3 million regressions, but they're basically all bullshit. So this is something that we have to take into account. And the approach seems to have an affinity towards statistical significance, which is problematic in itself. And something that we are discussing is just the relation between like the preferred model and the multiverse. How do we deal with that? Yeah. Okay. Well, yeah, thank you very much. That's it.
Okay, wonderful. Thank you so much, Reinhard. We now have roughly 20 minutes for the Q&A. People in the room, please just raise your hand. Those online, you can either raise your hand in the Zoom chat or post your question in the chat, in which case I will read it out for you. Okay, who wants to go first? Yes, please.
Yeah, thanks a lot for the interesting talk. I'm just wondering, in what stage from your analysis or research you decided I'm going to adopt this method, or from the very beginning you knew, wow, pursuing this approach, and how did that change? How did you see the effects of this, the impact of this, actual analysis or actual process? Yeah, when did you decide to adopt the approach? Or say we're gonna do this, and what are the implications that you saw in actual work?
I think we decided, Joanna, I think we decided. For this paper, we started out with it.
Mm-hmm.
So, yeah.
Maybe like a year and a half ago.
Yeah. It makes things more difficult.
That's encouraging.
It makes it more difficult in the sense that but I think that's a good way. I think that's a good thing, because it makes it more difficult, to tell a story. I personally, I'm not really convinced that this storytelling is a good thing. So yeah. That's just my opinion. So I mean, we have these, yeah. So yeah, it makes it more difficult.
Okay, then.
So I have two questions, one related to point 3 and one related to point 4, I guess. So, I mean, even if we, like, you have a specification curve where everything is statistically significant, and let's assume away the problem that you're measuring your outcomes and you're expecting on different scales. So let's assume we're on the same scale, right? But what if your betas still vary in size a lot substantively? Right? In the end, we don't just care whether the effect is statistically significant, which is also an effective sample size, right? We care about, is it important or not? And I mean, it seems to me if you're in this case, right, where you're like, my effect could be really small or it could be really large. I don't know, you're sort of just throwing it your hands in a way, and I don't really know how to adjudicate that. To maybe get to my point 4, which is, you do have a preferred model. It's not that your priors are completely sort of empty, right? You do have a preferred model for a reason. And if I were to use this, I would still in the paper present the preferred model and then only use this as sort of in the appendix as a robustness check to sort of to more systematically present the robustness checks that would have done anyways. Like I wouldn't present the sensitivity analysis as sort of the main results section of a paper. It would be, I don't know, for me it would be sort of too maybe messy in a way. I wouldn't know what the main takeaway of the paper is.
Yeah.
I mean, I don't know what you guys are planning on doing when you write up the paper. Would you?
I think my co-authors would prefer to have the preferred model. So yeah. Yeah. I mean, yeah, we could still present the range of the results from like those specifications where we fix our preferred specification. So if we are undecided on, let's say, 2 or 3 dimensions, we can still fix the rest, and then we will have a smaller range of betas, which might also answer your first question about the size or the variation, the variance in betas. Yeah.
Next up, we have Camille and then Malte.
Thank you. Maybe to add on this point, like, what are your plans with all these analyses? Is it then for the appendix of a paper, or where could I incorporate such analysis in a short paper? Because yeah, it's very complex. That's the first question. And the second one is, how would I decide which specifications I want to look at? How do I decide I want to recode variables, I want to do another, I want to use another algorithm? How do I make the decisions of how many specifications I want to try out?
Okay. Yeah. So I cannot give you an answer to your first question, where you want to put it. So far, I have to admit that or my experiences with reviews where I have used this method have been rather mixed. Well, so and yeah, and the suggestion to use it more or less as a systematic robustness analysis, this has come up. So maybe I have to curb my enthusiasm and accept that this is the way forward. And with regard to your second question, which specifications, I think there is no definite answer to that. I mean, you are the expert on your research questions, so I think you know best where there is a forking path, where you make one decision that could have also been made in another way. I don't know. I mean, there are numerous things. I mean, yeah. So So I think the difficult question, and there is room for improvement here. The difficult question is which decisions are really important, critical, or which make sense. Might not be that important to exclude respondents which are younger than 18.
Yeah, thank you. I was kind of intrigued and kind of skeptical when I came here, fearing that it's like you have like some algorithm that optimizes BIC and no one cares about substantive issues anymore, but you rule that out quite quickly. The question that I have, if you have models, if you have multivariable models, all your coefficients affect the other one. So you have covariance with your model specifications in your estimates. This might be a way also to decide against certain combinations if you can see, well, this parameter combination doesn't really make substantive sense. Like we typically always observe this thing to be negative, now it's positive. This doesn't feel right. But it's of course adding much more complexity. Could you comment on the opportunities and challenges maybe of this covariance of estimates?
I haven't really thought about that. I have to be honest. So at what covariance do you want to look?
Can't remember examples from your model, but if you, I don't know, if you have like the effect of attractiveness and you have like a control variable in there, like standard control variable, and with one specification, your sign in your main treatment flips, but also the other sign flips. And this doesn't really make sense that both of them are negative. Okay, something like that.
But this would be hard to tell a priori, wouldn't it? So
yeah, sure.
I mean, it's probably just another way of looking at the specification curve, isn't it? Because I mean, there you also see like how these dimensions interact.
Like in specification heat map.
Yeah, something like that. Yeah. I don't know. Yeah. But it's like it's a multi-dimensional heat map, so it's And I mean, for the first part, I mean, there are approaches out there which do it this way. I mean, they like look at the root mean square or whatever, and then, but I don't think that's a good idea because just have model fitting in. Best fitting model is not necessarily the correct model. So yeah, doesn't make a lot of sense.
Right, do you have any more questions or comments in the room? There are none online, so I'll put myself on the list. Thanks for the talk again. I'm still a bit hung up on the question that Nan also raised about how much do we care about substantive magnitude of effects as opposed to statistical significance of effects. And let's, like Nan, let's just disregard those scale dependencies that come from trimming or transforming the relevant predictors or outcomes. It seems to me that the method that you presented for analyzing variation in magnitude, where you essentially use your many estimated betas and then regress that on the design choices, gives us a lot of insight on obvious choices when we have those scale dependencies. But perhaps it would also be more interesting to see how that, like what sort of effects that unfolds within those sets of different measurement sets, so to speak. So how much do these decisions actually matter within the subset where you use trimmed earnings and a binary variable? And obviously that's something that you can do. You just have to subset it and run it repeatedly. But I was wondering, wouldn't it also be interesting to run this analysis on some measure of significance to see which design choices determine whether findings are statistically significant or not? And if so, what would be the measure that you would suggest we use? Would it be the p-value or something like a t or z statistic?
I mean, it would have to be the p-value because the statistics differ from model to model. So I would use the p-value. And I mean, this, yeah.
And maybe a follow-up on that. Would you recommend using p-values for directional hypothesis tests or a two-tailed test? Because it seems to me when you focus on the p-value only, what you miss out on is signs flipping. Whereas with a directional test, you could capture that quite well, right?
Yeah, that's a very good point, actually. I mean, if we have directed hypothesis, then it would make sense to. We don't have, I mean, we have competing hypotheses in the paper, so it's not case that's.
But I mean, if they're both directional, that
That's
a problem for
that's true. Yeah, that's true. I mean, again, with regard to the substantive importance of the effect, I think this is not a problem that is unique to this approach. I mean, I think we can still talk about the substantive importance or the substantive impact of something, even if we conduct a multiverse analysis. I mean, we do have a range of values. We can say something about you can use the range, and so I think this is I mean, I see that this might get lost actually. Yeah. So maybe it's the robustness, the systematic robustness of that.
All right, any more questions or comments? In that case, once again, thank you so much, Reinhard, for this excellent topic. And the Social Science Data Lab will be back with the final session of the semester on May 17th with an input talk by Hanna Bucher and Axel Burger from GESIS on the GLASS Open Science Challenge 2021, a pilot project on the applicability of registered reports in quantitative political science. Thank you all so much for being here today, those in the room and those online, and we hope to see you next time. Enjoy the rest of your day. Bye-bye.